again, we are going to be interested in point-taking numbers. Well, point-taking numbers. Well, here we have a definition of the point-taking numbers. We are considering a 4n-dimensional smooth compact oriented manifold, and as before, we are considering a partition of n. Well, here we have a very, very similar formula as we had before. This is this is the expression that we need for a point-taking number, and again, mu sub this sub-index, that is the dimension of the manifold, is the orientation class. It's the fundamental class. Well, very important in what follows are going to be the point-taking numbers of the projective space. There you are. You have the point-taking numbers of complex projective spaces, and that's a surprisingly neat formula that exists for computing the point-taking numbers of a complex projective space. And well, a very, very relevant issue in the context of finding Cobordism groups, particular oriented Cobordism groups, is to consider what happens when the orientation of the manifold is reversed. So let us stop here for a moment. Say, for example, that we are going to be considering an oriented manifold, say M for M. And we also want to be considering at the same time the same manifold, but this time with orientation reversed. The point-taking classes don't change. So that I'm going to write down. This is going to be equal to the point-taking classes that we are going to find . Point-taking classes don't change, but the fundamental class changes orientation, because that's precisely what we are doing. The fundamental class or orientation class here is going to be say plus, and here is going to be the same but minus. So point-taking classes stay the same, but the orientation class, the fundamental class, changes sign. So what happens when we come to compute the point-taking numbers? Well, if I write this down, we can recall from the definition that we had a monomial in point-taking classes. Evaluating this against the orientation class gives us the point-taking number, the ith point-taking number. Well, if I write this down again, but for the differently oriented manifold, I have to change this sign here. So the point-taking numbers are not going to be the same. And that is very, very relevant, because if we reverse the orientation of the manifold, point-taking taking classes remain unchanged, point taking numbers change sign, because we change the sign of the fundamental class, and as a consequence, if some point taking number is non-zero, then that manifold does not possess any orientation reversing diffeomorphism. And very, very interestingly, the point taking numbers of the complex projective space, the even dimensional one, are non-zero. Well, we saw that they are non-zero because we saw that we have a little formula here for computing them. So if we compute it, they are non-zero. And because of all this that I have been talking about, even dimensional complex projective spaces do not have any orientation reversing diffeomorphism. And that has some nice consequence for Cobordism, because, well, if some point-taking number of a manifold is non-zero, then it is not the boundary of a 4n+1 dimensional manifold. And, well, we already know that these point-taking numbers are not zero, so that, as a consequence, these projective spaces cannot be an oriented boundary. So if we begin to put things together, we see that all this has some consequences, and that means that if these projective spaces cannot be an oriented boundary, then they have to be generators of some Cobordism groups. Well, and there you are. Then we have a very nice definition of our oriented Cobordism groups. Well, especially very, very nice is this part over here. So why is that part over there so nice? Let's see. Here we have a table of computations, and here we have, well, these are unoriented Cobordism groups. These are the oriented ones that I'm talking just about, and we see that, well, some are zero, some are Z, and some are Z2 or Z2 plus Z2. And when I write this, it's clear, it's the direct product. So, well, the four-dimensional, the manifolds that are multiples of 4 in dimension, like this one, we have that finitely generated infinite group, and if we go to 9 to 8, we also see that these are 2 copies of Z. If we go to 12, this mistake here, this is 2 is missing. This 2 is definitely missing, because it should be 3 copies of Z2. If we look at any other dimension that is not 4K, then we see that they are finite groups, and we see that they are always copies of Z2. That was a result by Wall. And, well, that's it. It's very nice, because if you're only computing the oriented Cobordism groups rationally, then it's very, very straightforward. You only have to think about your generators. So, for example, if you get to n equals 8, then you have 2 copies of Q, and which should be the generators here? Only just these are the 2 generators, and so on. I mean, for the numbers that are multiples of 4, it always goes on like that. These are the generators. So I think we get to get a break here, and afterwards I talk about the signature. Questions?
Where did that table come from?
Oh, well, that table, it's in Milner-Stashev you have a computation of these groups, and in Andrew's book it's also there, although it's a bit short, I think. I think he computes up to 8. But I mean, it's a computation that you can find easily. And, well, I didn't mention it. I think I didn't mention it either the other day. These goes a bit differently, and it's also quite straightforward to compute, because the unoriented Cobordism groups these are the non-dyadic partitions of the number. So you only have to be a bit patient and compute your non-dyadic partitions, and you have your groups.
Of the high diagonal group.
This
I
here?
think, yeah, that's fine. I think you said something about CDC.
Well, oh, you mean the thing I thought about Terry Wall?
Yeah, yeah.
Yes, he proved that that when you're considering a dimension of the manifold that is not a multiple of 4, then we know that the group is going to be finite. But what he showed is that it's going to be either set 2 or copies of set 2. It's not an easy proof there, but it is there.
What kind of material is it?
Oh, lots of standard algebras and quite a lot of homotopy theory. Well, quite complicated. There's a very nice paper about computing Cobordism groups, and well, it was Wall who did that, but quite a long time ago. These results are from, I think it's from something like mid-50s.